This is the video lecture on Laplace transform method of solution of electrical circuits for transient response. Okay. So Laplace transform method is a method of solution of differential equations actually. As in the analysis of electrical circuits, we are getting differential equations in the form of KVL or KCL depending on the circuit that we have seen. The differential equations so far we solved by conventional method, that is determination of complementary function and particular integral. This method, conventional method, suffers from some drawbacks. As we have seen the method, those drawbacks are this. You see here it is mentioned. Transient and steady state solutions are to be found out separately. We did like that only. We first of all determine transient response and then steady state response. So two parts we have to do the solution, and the method is not systematic. First we have to determine transient steady state response, then again we have to go back to the initial conditions. Why? To determine the arbitrary constants, we have to go back to the initial condition. Like that, the method is not only lengthy but also not straightforward. That is the reason why there is a much interest on the another method called Laplace transform method of the solution of same differential equations. This method can be outlined or explained with the help of this scheme. This method actually consists of transforming the network into S domain from time domain. So that is the reason why this is transform, Laplace transform, transforming the network and corresponding variables equations from time domain to frequency domain, that is S domain. We are transforming this by using Laplace method. That is the reason why this is Laplace transform method. The method can be summarized like this. First of all, we will be getting this integro differential equations. If RL circuit is there, straight away we will get differential equation, we have seen. If RLC circuit is there, C also present, then we will be getting integral term and differential term. Like that, integro differential equations have to be first of all written, that we know. Next, these integro differential equations, if we apply Laplace transform, they are transformed to algebraic equations in S, that is frequency. S means here complex frequency, we have seen in the previous unit also. S, complex frequency. So all the equations are transformed to S domain. They are simply algebraic equations. There will be no differential term or integral term. They become simple algebraic equations in S. These equations are then can be manipulated into a suitable form. For example, if you want to find out the current, from that equations we can express the current in terms of other variables, like that. So if you do so, we will be getting revised transform. Revised transform is nothing but those algebraic equations written in revised form. So these two are the steps. First, apply Laplace transform. We will be getting equations in S domain. These equations are to be arranged as per your requirement. Okay, and the solution. For example, if you want I, we have to write expression for I. So that I will be in S, in terms of S domain, frequency domain. These are to be converted back, transformed back to time domain. Why? Because the answer, we need answer in time domain, T, whereas here S domain. So these S domain answers or expressions are to be back inverse transform into time domain, and that process is called inverse Laplace transform. If you do, or if you apply inverse Laplace transform, you will be getting the equation solution in time domain. This is the required solution, like that. Though it may appear that the process is lengthy, that is transforming to S domain, simplification, and again applying inverse Laplace transform. Though it appears to be lengthy, but we can see later that this method is very convenient than this classical or conventional method. This is not straightforward method that we mentioned already. So this Laplace transform method is like that we can perform. So that is about the Laplace transform method. Now we will see, all of you, the definition of Laplace transform is this. Laplace transform of a function f of t, denoted as f of s. You see, time domain into s domain. So this is the Laplace transform. So Laplace transform of any function is written like this and represented like this, f of s. This is given by what? Integral 0 to infinity f of t e power minus st dt. Actually here we are getting 0 minus. That is, see, to include for, this is included for impulse function. That is very special function. Impulse function will exist only from 0 minus to 0 plus, that's all. For other values of time, the function will not be there. In general, we can take this as 0 to infinity f of t, function f of t e power minus st dt, where s is here complex frequency. The real and imaginary terms of complex frequency we have seen. Real term is Neper frequency and imaginary term is something we defined, radian frequency. So that is yes. So that is the definition of Laplace transform. If we apply that formula or relation, we can find out the Laplace transform of any time domain function. For our purpose, we need the Laplace transform forms of some important time domain functions that we frequently encounter in the solution of networks. Not only these, for any function we can determine the Laplace transform. I hope that you might have done in your mathematical course. So all those are summarized here. You can see this is unit function. Unit function means 1. Laplace transform of 1 is 1 by s. V, you see here v is written as v into 1. U of t means you can take it as 1. U of t means unit function. Unit function means its value is 1. So u of t or 1, both are same. V into u of t means v into 1, v. For that Laplace transform will be v by s. For 1, 1 by s. For v, v by s, like that. For t, 1 by s square. Laplace transform of t is 1 by s square. Laplace transform of t power n is this. And this is required for us. Laplace transform of sin omega t equal to omega by s square plus omega square. Laplace transform of two functions can be added like this. This is nothing but sum of two functions in s. And this is important. Laplace transform of derivative of the function d by dt of f of t is given by s, f of s, s into f of s, Laplace transform function f of s minus f of 0 minus. This is initial value, the function initial value. So like that, the initial values are automatically included in the Laplace transform. Like in the conventional method, we need not find the initial values separately. Initial values are all automatically included in the transformation formula. So these are. So this you can remember, d by dt of f of t can be written like this, s f of s minus f of 0. This is first order. Second order derivative of the same function is like this. You can compare this and this, s square f of s minus s f of 0 minus f dash of 0. This is the derivative of the initial value. This is initial value and this is the derivative of the initial value. So like that, we can list out some time domain functions and their Laplace transformed values, transformed functions. So that is about a Laplace transform. That is in general, as you know. Now, how to apply this method to our circuits? That we have to see. You see here. If we want to apply Laplace transform method to our electrical circuits, the first step is to draw the transformed network. Transformed network. We know what is transformed network. That is given in the previous unit. So if the network, all elements of the network are replaced by their transformed impedances or admittances. All the elements in the network are replaced by their transform impedance or admittance. Then we will get transformed network. In representing this table or the summary is useful. You see, R is the element that will be in transformed network becomes R only. R is R, no change. In impedance form. This is for impedance form. We use impedance form of representation for series circuits. And we use admittance form of representation for parallel circuits, pure parallel circuits. If you are solving a parallel circuit, then replace R by 1 by R for transformed network, like that. Next, for L in series circuit, this is represented as LS. So for L, transform impedance is LS, transform admittance is 1 by LS. Admittance is nothing but 1 by Z, 1 by impedance. So this is. Similarly, if C is there, that is to be written as 1 by CS in series circuits and CS in parallel circuit. Now same L, if it has some initial current like this, you see, here there is no initial current. That means L is fresh, no initial current. Whereas here, this is used inductor. It has some current in it initially. If the inductor has initial current like this, then it is to be represented like this. Not simply Ls by, but Ls in series with a voltage source of value L into this value IL of 0. L into that initial value, like that. And this is the representation, same L for parallel circuit. C also. If C has some initial voltage V of 0, here C has no initial value, initial voltage. But if C has some initial voltage, it is to be represented like this. Okay. In impedance form, 1 by CS in series with a voltage source. Here also. This is for admittance. So like that. These are very important. In series circuits, R is to be represented like this, L is like this. If L has initial current like this, C is like this, and C is, if initial voltage is there, it is to be represented like this. That is the first step. And after that, in the transformer network, we need to express either I or voltage or anything what we require. Okay, we will see an example. This is the circuit. So what is the circuit here? It is having R, L and one more resistance R. It is given that the switch is in position B, this is B, for t less than 0, that is t equal to 0 minus, before switch is closed at t equal to 0. The switch is in this position. This position means circuit is this. And sorry, not that. You see, we are wrongly saying. You see, what it is mentioned here, at t equal to 0, switch is moving like this, down arrow, like this. That is, at t equal to 0, switch is moving to this position B. Okay. That is, before t equal to 0, what? The switch is in A position. That you have to understand. I said it in a reverse way. Before t equal to 0, switch is in A position. That is the meaning, isn't it? Why? Because the movement is downward. Downward means B, towards B. that is at t equal to 0. Before to that, this is in A position. Okay, so that is the case. Before to that means what is it meaning? Before t equal to 0 means t equal to 0 minus. It is given generally to determine the initial values. Initial value means before t equal to 0. For that, switch is in A position and we can draw the circuit and we can determine the initial current that is required. You see that current is 1 ampere. What is that initial current? This. Why it is 1 ampere? Before t equal to 0, that is t equal to 0 minus, switch is in A. A means this, like this, 10 volts A, and then 10 ohms, 4 Henry, and then supply back. This is not there, only A is connected, and the supply is DC supply, and it is there for a long time. Then inductor will act as short circuit. Don't confuse, I said so many times in the DC transients. This will also come under DC transient. DC supply, inductor, and that supply is in A position, that is connected to the circuit for a long time. Means inductor is short circuit. If inductor is short, then 10 volts and resistance is 10 ohms, that's all. So current equal to V by R, 10 by 10 only, 1 ampere. That is given here. Also like that, at t equal to 0 minus, as switch is in A position, we found that current in the circuit, that is nothing but initial current, equal to 1 ampere, that determined. So in the problem, initial current is given. Given means we determined that element. At t equal to 0 minus, current is 1 ampere, means at t equal to 0 plus, what is the current in inductor? 1 ampere only. Inductor before current equal to immediately after 1 ampere only. So the case now is inductor with some initial current. Okay, inductor with some initial current of 1 ampere. That you have to remember. Okay, that's all. Now what happened? At t equal to 0, switch is moved to position B. After that, what is the current in this circuit, that we have to determine. So for what we did, initial value before this. Now switch is moved to this position. This position means circuit is this only this. This voltage source part disconnected, only this. Now whatever may be the energy stored in this inductor will be discharged to this 2 resistors. That will be the case. Current will be there, though there is no voltage, current will be there in the circuit. Why? Previously inductor was acquired some energy, though it is shorted, but current is there. Because of that, it acquired some energy. That energy will dissipated in the circuit like this. So that current is this, and we need to find out that current. Okay. Now Laplace transform method, that circuit at t equal to 0 or t greater than 0 is to be represented by transformed circuit. R is R, L is Ls plus something, and C, if C is there, 1 by Cs, like that. So after t equal to 0, this is the circuit having 10 ohms resistor, and 4 Henry inductor with initial current 1 ampere. That is the circuit. Transformer network is this. This 10 ohms resistor is replaced by 10 ohms only. And this is series circuit, means series circuit. Series circuit means we represent all impedances. These are all impedance form. R is R only. Okay, therefore this 10 is 10 only. And this 10 also 10 only 10. And this inductor 4 Henry with initial current, you see, inductor with initial current, how it is represented? Ls in series with a voltage source. This here also Ls, L means 4, so 4s in series with initial value. Initial value is L into I naught. L means 4, I naught initial value 1, 4 into 1, 4. So that is the case. So L is represented by Ls in series with some voltage. So this is the transformed circuit. And in this circuit, we need I. You see here, this is transformed network. That is the reason why I here, time function, is represented by IS, is written as IS. Why? Because it is transformed circuit. This is IS. Now from this circuit, what is IS? This is nothing but, this is voltage V by total impedance. Total impedance means 20 plus 4S. 10 plus 10, 20 plus 4S. V by 4S. V means 4. 4 by 20 plus 4S. That is the current. Okay. What is I here? I is nothing but V by total impedance. Total impedance means 10 plus 10 plus 4S. 20 plus 4S, IS equal to 4. Or IS equal to 4 by 20 plus 4S. If you simplify this, 1 by S plus 5. So this is the expression for current in the circuit in S, IS. This is IS. Now we need the value of I in time domain. So therefore what we have to do? Method. See, here I is this. This is to be transformed back to time domain, inverse Laplace transform. That we have to apply. IS equal to 1 by S plus 5. Inverse Laplace transform of 1 by S plus 5 is nothing but e power minus st. E power minus 1 by S plus a. This is in the form of 1 by S plus a. A is 5. So inverse Laplace transform is e power minus at. That is the case. So this is the answer. I of t equal to e power minus 5t. So like that, by transforming into transformer network and writing expression for I or V or anything, this is the expression. That expression is transformed back to inverse. Here it is simple. We simply transformed. If we get a big expression, then the inverse Laplace transform involves some procedure that you know, partial fractions and what you know, some other functions are there that you have studied in mathematics. By using those, we have to apply inverse Laplace transform. That is only the difficult part here. Application of inverse Laplace transform. Like that. You see now another circuit, RLC circuit is given with DC voltage of 8 volts. What we did, we simply replaced by transformer network. Here initial conditions are not given, whereas in this circuit initial conditions are indirectly given as which is in A position, but here not like that. And in the problem also no initial values. Initial value means no initial current on inductor and no initial voltage on capacitor, not given. Therefore inductor initial current is 0, capacitor initial voltage is 0, that we can take. With that in mind, we can now draw the transformer network. You see, this is also series circuit, therefore all impedances 4 resistor, 4 only, inductor L, Ls only, 1 means 1s, 1s. No initial current means no voltage, only Ls, that's all. Capacitor also 1 by 4. C is 1 by Cs. If you do 4 by S. Cs. And 8. 8 is transformed as 8 by S. For V, V by S. For 8, 8 by S is the transform. So this is also transformed. Like that all are transformed. That is the reason why this is transformed network. I is also IS. Right. So this is the transformed network. Now in this transformed network, I is nothing but what? V by total impedance. V means 8 by S divided by 4 plus S plus 4 by S. This is, that is I. If we simplify this, this is equal to 8 by S plus 2 whole square. You see here. Now the expression is somewhat big, not as simple as this case. Here it is very simple, directly we have written. But here I of s equal to 8 by s plus 2 whole square. You know how to determine inverse Laplace for this. This is one of the method. I am not explaining this. You can try it by your own mathematical methods. If we apply inverse Laplace transform, finally we will get this is the expression. For 8 by s plus 2 whole square, inverse Laplace transform apply I of t. Here I of s. After inverse Laplace transform, I of t. Final answer. That will be 8t e power minus 2t. This is the expression. Okay. In obtaining inverse Laplace transform, you simplify it as much as you can. No need to get final expression. After this, you simplify as per your capacity, or 3 or 4 steps. That itself is enough. If it is a big expression, you need to do something here, more steps. So whatever you can do. So you will get almost very good marks. Only for answer only 1 mark or 2 marks will be considered. For that procedure you will get good marks. So that is one circuit. And this is parallel circuit. Okay. Here for parallel circuit, we represented in transformer network all admittances. You see here at t equal to 0, switch is open. If it is open, then only I will be connected to the supply circuit. If it is closed, that is before t equal to 0, I is shorted like this. That is no supply, no current supply to the elements. At t equal to 0, what is happening? Switch is opened, removed, switch is removed. Then what happens? This I is connected to the circuit. That is happening. So that is the circuit after t equal to 0. As it is parallel circuit, we represented all admittances in the transform network. R is 1 by R, L is 1 by Ls, and C is Cs only. Like this is the expression. Now as it is parallel circuit, we need to write KCL equation. This is KCL. Whereas in the previous case series circuit, we have written KVL. This is KVL. The series circuit, KVL. Parallel circuit, KCL equation. This equation also simplified. In parallel circuit, we need to find V, voltage, circuit voltage, that is this, and this can be simplified, not even here. This can be simplified. Vs will become 2 by s into, this will come this. After that, inverse Laplace transform, V of t, you have to obtain. So that is the case. And here there is no difference of DC circuit or AC circuit. Once transform is applied, all circuits are equal. That is the another advantage of this Laplace transform method. Okay. Only thing is you need to write the transformed function for the supply. If it is DC supply, we will be getting V, and in transform V by S. If I is there, I by S. In AC circuits, if the supply is this 20 sin omega t or 20 sin omega t plus phi, corresponding Laplace transform will be this. That's all. If it is only 200 by S. But here AC supply means 200 sin omega t, 500 t. So the transform, Laplace transform of this 200 sin 500 t is this. That is only the thing. Same, no change. This is the KVL equation, and the transformed equation of this is this. We have written KVL equation. For that we applied transform. Circuit is not shown, that's all. If you see the circuit, then this is the KVL of the circuit. From this I of s is written. This is I of s, and this is to be fractionized like this to get the inverse Laplace transform. And the inverse Laplace transform after simplification will be like this. This is the expression. So what I said previously is, you see, this can be simplified to this. e power minus at can be written as sine function or cosine function, like that. You need not simplify all these things. If you can write this, that itself is enough. This is further simplified. This e power terms are represented by cos and sine functions, and they are all again simplified and finally written like this. No need of all these things. You can stop at this step itself. That is the solution. So like that we can solve the circuits in Laplace transform method. For example, I have given 2 or 3 circuits. You can find more circuits and solution in any of the textbook. Okay, textbooks are plenty in the library. Just go to the library. Okay, you search for some textbooks. I am not mentioning the author. Why? Because you search for the textbooks. Whatever the textbook you find it easy to understand, you can follow the textbook. So many textbooks are available on network theory or electrical circuits. With this video, you can now go to the textbooks and do some other examples. Okay, that is about the complete syllabus of the network theory. Okay, if any doubts, you can approach me either by phone or by email or by WhatsApp. Thank you very much.